News on Unpeeled. So Fortify has received a strategic investment from Lockheed Martin Ventures, the VC arm, if you will, of Lockheed Martin. So Fortify is a US-based company that has a continuous kinetic mixing DLP process that is able to, in a coherent way within a DLP process, so get the detailed but give them proper other processes can. Initially, I was super skeptical about Fortify. I really actually wrote a quite critical article of them at one point because I really did, because their market was polymer injection mold inserts and tooling. I didn't think this was the right market. I really didn't think it would work, and I really didn't think this was an application that would really particularly work in the United States. So much of this tooling business is based in China, and really intense about the company coming up with this technology and then all of a sudden using it for these mold inserts. This is an interesting market for 3D printing, but not in the particular way they were doing it and the market they were targeting. But there was one thing that I wrote about previously a couple of times that I was very excited about, and that's about RF technology. So radio frequency components. And at one point, a lot of people were trying to make waveguides and other RF components using 3D printing, additive manufacturing, and these alignment of these structures could pose for very optimized materials. Now, at one point, the company did do a project with the Rogers Corporation with these, but they put dielectric ceramic additives inside the DLP prints, and they made essentially a high performance dielectric material in a particular very, really specific shape that was optimal for these kind of RF components. So this has huge potential, and I think that Lockheed also recognizes, and that's why they invested. I mean, the RF devices market is exploding, literally and figuratively. So you're seeing that there's lots more things on the battlefield. There's lots more things operating all over the place, and there's a constant need to know where everything is, and to communicate with satellites, and communicate with other communication systems, and to use targeting systems and force protection systems. And at the same time, there's kind of an arms race going on, kind of a quiet arms race about jamming these things and encrypting, sure that all these signals can't be triangulated in the right way, and making missiles that have RF components on them, and making missile defense systems that make use of this or that protect against this and that kind of thing. So this market is really, there's a kind of battlefield going on. One of the ways battlefields are going to through these components that we're communicating everything through waveguides and conformal antennas and all sorts of structures like that. So I think this is a wonderful investment for Fortify. I think it's a much more fruitful path forward than these mold inserts. And I think this could be, if they get the performance there, this could be a huge market for them, because the number of things that need RF sensors or RF kind of antenna on it are going to only get bigger as the communication needs and video and satellite communications increase. So it's a good move for them, I think, Lockheed investment. The next thing, we're also seeing kind of optimization through shape kind of things from Conflux. Australian company Conflux is a heat exchanger specialist. They got started in racing and things like that. And they then did projects where they would work with like an automotive firm, for example, to make the best heat exchanger. Of course, that kind of project is like, it takes a long time, especially in automotive. So now they've begun developing kind of mass customized heat exchanger, customizable heat exchangers. So they make like a reference design, the shapes should let you adjust it. The idea being that then very quickly they can get images out there part very quickly. They can sell this to a customer. So it's essentially product velocity, right? Parts quicker, and just everything will be accelerated. And this is like a Conflux cartridge. It's a very, very compact part that is easy to service, swap out, and it's designed for maintenance, which is a thing I really, really like, because we're designing for optimized parts. But of course, maintenance engineer, like 50 or something, is going to really add to that cost. And it's an easy to configure component that can give a lot of heat exchanging to manufactured component. So you can add this cartridge, if you will, to a conventional component. Generally, this is like another example. We can also increase, we can also change the properties of this part, or change the way this part is designed throughout where in the heat exchanger, the liquid or the fluid or whatever is flowing. So we can really optimize this design. And I think, the world is waking up to the fact that heat exchangers is one of the most exciting and fast growing areas of additive right now, where we're making high performing components that are outperforming traditional heat exchangers, and that are delivering value that offsets the cost of 3D printing the component. So really, really great area, and I think, and Columnflux is really showing the way with these mass customization elements here. This next thing, it seems like it's a fanciful thing initially, until you look a little bit deeper, and it might be a huge market. So there's an architect, a company called BVN, and they worked together with the University of Technology Sydney to make quite a different air conditioner. So air conditioners are, there's about 1 billion of them worldwide, and they may grow to 5 billion units over the next 20 years. Air conditioners also consume a lot of electricity. Some calculations, about 10% of electricity is used for lighting and heating and air conditioning for buildings. It's a huge amount of air conditioning. And we could kind of get caught up in a kind of an environmental kind of death spiral with air conditioning, right? As air conditioner use increases, they use more electricity, right? They're used more. This is Jevons effect, right? Where they're used more often and they become more common. And then there'll be more and more. That will then lead to more and more air conditioners being used. More and more air conditioners being used leads to more power usage, which will lead to a further warming of the earth, which will then cause people to use more and more air conditioners. And so we can go into kind of an air conditioner death spiral, if you will, and then which is hugely damaging. Again, if these things are true, you're talking about 1 billion units, and then expanding to 5 billion units. That is an incredibly big market. So there's an environmental reason for why we should look at this, and also there's a commercial reason where any kind of solution in the space could be really very, very commercially successful as well. So I love that there's other things going on in heat pumps. There's a few companies kind of looking at this, but not enough, I think, and not enough given the potential. So this system, which you can see in front of you, is called the Systems Reef 2. It's recycled polymer. I think FDM made in a desktop 3D printer, if I wouldn't guess correctly, just looking at the part. So recycled, and it's a design optimized part that uses less energy in the system than a conventional solution. So what it's replacing is the things that you always see your action heroes crawling through. They're actually kind of a bit smaller, but the air conditioning ducting. And the air conditioning ducting is made out of sheet metal parts and have been made like this for a very long time. What these guys have done is something that is blindingly obvious and at the same time wonderfully creative. And they say, look, what if we optimize this design and we don't do as many kind of right angled corners, but we make it a much more organic design where energy can flow through it in a much better way. Now, wouldn't that be a lot better kind of a component? Wouldn't that be a lot better way of making this work? Right now, the idea is that not only is it less energy to make this when compared to like the static one, but also the energy consumption will be lower at the same time. What the team also says, which I thought was something really to ponder, is that these things have been designed a very, very long time ago, and not necessarily to optimize the comfort or energy flow or anything like that, or airflow even, but just to be to within the paradigm of manufacturing that existed back then. So this might be a market that's really ripe for disruption. So they want to limit air getting stuck in corners. They want to make that air flow a little better, and at the same time, they're doing something else, which you can see here in the next slide, where they're taking and making smaller kind of pores. So rather than have these big vents that blast out air, what they want to do is have these smaller pores that kind of mist out air a little bit more in a kind of misting kind of way, which they say will be better at cooling them. So I love this. I think this is a really wonderful example. I don't know if this is going to make it, but I think that this is something that really deserves a lot more attention. And yeah, so that could be really very, very exciting.